I'm going to talk regarding image acquisition, image sensing, some simple image formation, image model, some typical range of illumination, some reflectance, and so many things that you can see here. Maybe I will put some part for the next lecture, but I will try to cover all as much as today we can continue to see due to the time restriction that now we have. First of all, to work with the image, we should see the source. Source of the image in the sense that how we will acquire the image and how it will happen to having the picture. Means that initial part or initial box of our image, this is the image acquisition system. Image typically generated by illuminating the sense and absorbing energy which reflected by the sense object. We will talk last lecture about the light and how it will reflect the object. But now we go for the image. You know that there is some words which is highlighted in this sentence. One is the illuminating and another one is reflecting, which initial part of today I will talk more regarding these two concepts. Here it can be the system. You will see that we have the source which will be illuminate, or we can say that some sort of the energy which will be put or reach the elements or any part of the things that we know. And then we have some image system, which this image system will be reflect or will be show the object that we have. And then our job is the another box that you can see here. We want to make it digital. There is some nice thing as you see. There is grid. But this grid is exactly based on the matrix idea that we have. I mean that if you see this grid as the you see this grid as the matrix form X and Y in the X and Y direction, or having the row and columns, then you will see that first object is showing there or monitored there in this sense, and then in this monitor, big monitor, and then it digitizes. And some nice thing is here. You saw that this digital image is not as same as the first image that we have, but it has the most feature or most similarity with this. What is our job? Our job is that make these two figures very near to each other. I want that you understand that digital image is not real image, because some color, some feature, and some part can be missed by them. You check in your mobile phone, you have the AI support or AI option. In the AI option, you will see that it's make your face even more beautiful than you are. But it's you, but it has some more feature or some less feature like that. And it can something like doing some job like makeup for your face. Well, this is the real concept of digital image. Then have it in your mind. Digital image is not 100% the main image, but our job as the engineer or as the person who work in the algorithm is that we want to make these two images as much as similar that we can. Maybe 99.9% we want to make them similar. Maybe 91.9999 like that we want to make them similar. But really, if I can say, there is some probability or there is some chance that this figure is not as same as the real sense or real image that we want. The old idea regarding the having the image is something like that. There was some pinhole camera. The idea is very simple, and I can tell you very nice, which you had one object with the distance in Z, suppose, direction, and X and Y you can see here. Then what will happen in the year 300 or 400 AD, Chinese and Greek people will invent this method to copy and having the image. And maybe still some painter use this pinhole idea, and you know that there is some math behind that, that it will show that in the X, we have the F divided by Z multiplied by X, and also for the Y, we have this. And you will see that the image is rotated, or it's 180 degree rotate. We have the rotation for 180 degree for our image as the receiver part or the monitoring part that you can see here. This method used for some of the painting and some of the artwork that previous time people will do before the camera is invented. And now we know that why it's invented, because our algorithm in our eye is something like that, which it will rotate the main object that we have. After that, they try to make it this object little bit bigger or smaller, okay? And then they use the lenses, and again, same idea come to picture. Some optical exists that we have through the lenses, and then the figure will be monitored as the ended part or as the monitoring part that we have. Then thin lenses come to the picture, and slowly these acquisition system grow up till the time that now we can have some image sensing or some method that can help us to acquire the data. Let us think and see this subject, means that image acquisition, like image sensing part, which in that we have some incoming energy, for example, some light, which land on some sensor material. These sensors are responsible to some type of energy, and then by that they will generate the voltage. Then this collection of sensors can, with this method, capture the image. What I mean that as the rough idea for acquisitioning the image, we can have some sort of the sensors that they are sensitive to part of the wave, part of the energy, and through that they can acquire the image. With this idea, then we can have some small image sensors like what I shown you here. It consists of some filter, some energy as the input, and some sensing material. This sensing material and this filter can be in different type and variety. And then, as the output of this part, we have some voltage which will be generate. Okay. Then you can put these sensors in the line format, or you can have them in the array format. Okay, and then having the different type of the acquiring systems. Then what we'll have? We have the transform illumination energy into some digital image. Then, in all summary, how we can have the digital image is by having some sort of this sensing material, and then generating the voltage like that. Let us see some image acquisition which they are using the sensors. We can have some assembly like that, which we are rotating and then moving the sensors in the linear motion, and then we can have the image. Maybe this part will remind you some scanner job which you will use for your photo, and you scan your photo, your ID card, with the help of that. And we call it the method which by that we can make the 2D image generation. Or you can have something like that have some sensor strips, which is exactly the scanner that we have. And you will see that when you will scan the image, this sensor image will go up and come down and then acquire the image for you. But today we are going to have thought more regarding the math behind this image and image modeling. Then let us have something like that. It means that the simple image formation model can be the equation like fxy is equal to ixy multiplied by rxy. Why we have xy here is that because we try to have the 2D concept regarding the image. Then, as we talked, we have some keyword. One was illumination, another one was reflectance. Okay. Then, in the equation that I give you, if we know the fxy as the intensity at any point with the x and y, please remember the grid that I show for you. Please have the concept of matrix about any image. You will see that this equation will be presented by illumination as the I, means that illumination at any point of x and y, or the amount of the source illumination which indicates on the sense. This is one part. And this illumination should have some relation or some mathematical form or some relation with the reflectance or transmissivity at any point of x and y. Is that the amount of the illumination reflected by the object, which this ix and y should be between 0 to infinity, and the r part that we have means that illumination is between 0 to infinity. This is the illuminating part that we have, domain of that. And the reflectance can be between 0 to 1, and it can be the wide range of the numbers. Have this in your mind. It's something like monochrome or of image model. As we talk, a monochrome or black-white image, it's something like 2D light intensity, which will be donated as x, fx, and y. And the value or amplitude of f of the function as any point of spatial coordinates of x and y is intensity of the image at that point. Then, as light, we can know it as the energy. The value is non-zero. Then f can be between 0 to infinity with the equation of fxy or function of fxy, which have the two components of I and R. I, as I said already, it's amount of light indicate on the sense being viewed, and R is reflected relating to the amount of the light reflected by the object in the sense. This equation I tell you already, but that was some complete concept regarding that. Maybe some brief review about that. Just have it in your mind that the monochrome model or fxy is the combination of the reflectance and illumination of the light or source of energy that we have, and we can present any model of image with this fx and y. Let's go more deep. Suppose for the monochrome image, the intensity of image f at any coordinated fxy, we termed as the gray level. And L of image at that point, we have the L between some minimum and maximum number, which it can be between 0 to the maximum value of L. What I mean that if you think the gray model or monochrome color for the image, this L can be at the minimum side 0, and at the maximum side it can be L. Then for the gray color, the minimum value can be black and maximum value can be white. Okay, then we can say that this L is representing between, or it has the domain between two values of the white and black at the minimum and maximum part. And some intermediate or some numbers between 0 and white can be as the gray or gray shaped. Anyway, that was the first part. But if we want to have some more data regarding illumination and some even more concept, which is really, this is more related to your physics subject, but I purposefully bring it here to make the concept from this word more clear. We can say that illumination will come with the one measurement definition, which we call it lumen. In lumen, which is the unit of light, which will be flux of or luminex flux, and we can have this definition that lumen per square meter, which they'll show it as Lm divided by M2. This is the metric unit to measuring the luminance of surface. Have this in your mind. If on a one clear day, the sun may be produced, exist of 19,000 Lm per square of illumination on the surface of Earth. And on cloudy day, this is 10,000 of this value. On some clear evening, the moon will yield 0.1 Lm multiplied by Lm per meter square. And in typical illumination level is commercial offices about 1,000 Lm divided by M square. I mean that in even single day, we have the different illumination value or lumen value, which obviously it can reflect or it can act on our image production or image output. That was for the illumination idea. Let's have some value for reflectance, and you will see that this reflectance is between 0.1 for the black, and for suppose for stainless steel reflection is 0.65. For the wall, it's 0.80. For the silver-plated metal, it's 0.90. And for snow, it's 0.92. That is why the value for the R, we expected that it will be between 0 to 1. And for the illumination, as you remember, the first formula that I tell you, that was between 0 to infinity. Okay, well, what we learned that the image will be affected by two things. One is the illumination, another one is the reflected. But now our work is something like digital imaging or generating the image with the digital methods. In that, we have two words which we will talk more today for these two concepts. My friend, be clear for this that when we say anything regarding the digital, suppose digital image, digital, I don't know, digital signal, any things which is related to digital, we have these two words with that. One is that sampling, and another one is quantization. Let us see what is this. Sampling and quantization will generate the approximation of the real world sense. That is why I tell you that really the image is digital image is not the exact image. We have some similarity between them, but the main thing is that with the help of these two words, we can see that really why the digital image is not the real image. See here, these two figures that I show. This is the main figure or main object. And another one is the digital form. You see that some part is not really clear, but it's very similar to real figure that we have, with the idea of matrixing, with the idea of column and row for the image. Let us see what is these two words, which we call it key stage in digital image processing. First is sampling, which is related to coordinates the value with the help of some theorem that we have. We call it Nyquist frequency. And another one is quantization, which is related to intensity value. Then for the digital processing, we assume that we have the image function of f, x, and y, which must be digitals, both especially and its amplitude. Typically, a frame is a Gerber or digitizer is used to sample and quantize to analog video signal. Hence, in order to create an image which is digital, we need to convert the continuous data into the digital form. Let's go more. What is really sampling? Sampling in the real world, it's something like cutting the image. As your book said, the digital sensors can only measure the limited number of samples as a discrete set of energy level. And sampling can be true as the continuous signal X, which multiplied by comp function, as you will see. If I want to give you some idea regarding the sampling, suppose you have one cucumber and you have one knife. If you want to sample it, you can cut this cucumber. And then with the help of this knife, you make the sample from that. If you push from both sides this cucumber, you have really one cucumber, but if you little bit separate them, you will see that it's becoming to the slice. Same job we will do in the sampling time. Sampling time is something like make the slice from the main wave, main image, or any other signal. It's something like cutting them. Then what is quantization? Quantization is the process of converting continuous analog signal into its digital representation. But see that we have some limits value, and here, as you will see, maybe we should have some technique to again come back to the main figure that we have. If we think for the sampling and quantization, we have two words. One is that sampling rate, which determine the spatial resolution of the digitized image. And quantization level is another one which determines the number of gray level in digitized image. The magnitude of sample image will be expressed as the digital values in the image processing, and the transition between continuous value of the image function as it digital equivalence, we can call it quantization. Then now we become fairly familiar the two words of sampling and quantization. Please remember that the number of quantization levels should be high enough for human perception of fine shading details in the image, and the occurrence of the false contours in the main problem in image, which has been quantized with the insufficient brightness level. Have these two critical sentences in your mind. Later we will talk more why figure is not good, why figure is not proper for our application with the help of these two words. Then, as the idea of X, F, X, and Y relation to obtain the digital image, we can digitalize both space and amplitude of this equation. Then digitization of a spatial coordination, we can call it image sampling, and digitization of amplitude, we can call it gray level quantization. The image sampling is viewed as the partitioning an image plan into a grid with coordinates of center of each grid from an integer sets of z by z. And the gray level as the quantization is viewed as assigning a value from the real number sets R as a gray level to each grid. If you see this figure, maybe it's become more sense for you. This is my real digital image. In the figure A, the continuous image we have. In the B, we have the scaling line from A to B in the continuous image, which used to illustrate the concept of sampling and quantization. And in figure number C, we have the sampling and quantization, as you will see here, C. Then in the D1, we have the digital scan line. Okay, this is the digitization that we have. And here we have the sampling and quantization, which from the same figure that we have. Let's once more see the previous image that we have. The continuous image projected on the sensor array, it's something like A, and B is the result of sampling and quantization work. I can say some digital work that we have done on that. See the image once more from this perspective or from this view, that image is nothing but 2D array of pixel value, and these pixel value are gray level, which will be between 0 to 251. We call it RGB. We talked already. And array value can be any data, which will be float, can be integer, can be double, and so on. Then this figure that I show you can be something like that. Suppose in this figure, the image plotted as the surface can be something like this. An image as the visual intensity can represent by the D form that you will see. And the C, we have the image shown in the 2D numerical array between 0.5 till 1, which is the representing the black, gray, and white value from the monochromic line. Now what we learned that how to acquire the image. Second one was that what should be the mathematical form of the image. Let us now have the real representation of the digital image in the form of matrix, which we can have same f, x, and y like this, like the value of 0 and 0, it's total dark, till some amount of the x and y, which we don't know really. It depends on the picture by picture, it will change. Then hence, resulting the image can be some matrix like M to N, in which each matrix element can represent the image elements or picture elements or pixel, as its value represents the gray level of that pixel. And see here, the number of sample or pixel we can have, m multiplied by n, required to approximate an image which we know it a spatial resolution of image. The low or insufficient spatial resolution result in pixel replication, causing the checkerboard effect. See here, this is my image, and this is the effect of the checkerboard effect that you will see. It's showing the picture, but the resolution is not proper. Maybe you saw it when you worked with some software like Photoshop and some other software like that. And then you may see that with this software, sometimes your image become like some checkerboard like that. But now we learn that why this will happen, which is related to number of sampling and quantization. The number of discrete energy level, G, we call it G, which is allowed for the pixel in digital image, and we call it gray level resolution of the image. The low or insufficient gray level resolution rate in rigged light instruction in smooth area, causing the false contouring. Let us see, suppose this image. You can see the effect of gray level resolution and false contouring. As you will see, suppose my 8-bit original image is here, then 4 bits, then 2 bits, and then 1 bit. Okay, as the binary image. You will see the quality here. You will see the, I can say the data which will be missed on the last image that I put for you. But then this is the idea that how should be this sampling and how we can have relation, some mathematical relation or some logic relation, how we should do that to have the good quality of the figure. These are something maybe arising in your mind that then what we should do with the figure. If we assume the quantization will be n, m, and then n and g are chosen to be the integer power of 2, something like equation like this, m 2 power by p, and n is equal 2 power by q, and g is equal to by r, where we can say p and q and r are any positive non-integer. Just assume this idea. Then the size of resulting image can be something like that. M divided by, multiplied by n multiplied by r bits can be the size of the resulting digital image. Let us have some exercise with this. Suppose what is the physical or what's the size of 8-bit? As you know, it has the 256 gray level. We can say that the image of 1024 multiplied by 720, B value is something like this much bit. If you have the 8-bit, we have the same calculation, but the value is this much bit. And as we know that 1024 bits are 1 kilobytes, is 720 KB, and 124 kilobytes are something like 1 mega. These things we know. Then we can calculate and see that the size of our image is something like that. Have this in your mind that using the different value of a spatial resolution, for example, versus as well as fine sampling and gray level resolution for a given image is known as non-uniform sampling and quantization. These are the concepts that we should know. Then maybe some people say that what is this spatial sampling? It's first of all, we should know that we cannot record the all image value for X and Y, and sample or recording value at some discrete value of X and Y can be the spatial sampling. And sensor arranged in a grid can sample the image. Suppose if it can be my X and Y, then L as the spatial sampling can be something like that, some grid like this. And after this process or spatial sampling and quantization, an image is discrete function which is related to the Q, and then it has the range of the I is that which is related to. More, if you want to talk, we can say that with this spatial sampling, we have the spatial resolution, which in that an image is determined by how fine or gross sampling was carried out. Spatial resolution, we can call it as the smallest discretable image details. And visual specialist talks about more about image resolution. Then we have one concept that all of you may hear that we call it DPI or dot per inch, which graphic designer most of the time speak regarding this DPI. See, I bring one image here for you as the spatial resolution. It's great. You see that this flower at the first and flower at the end, and you will see that the different resolution or different DPI in this figure. That was one more critical or more important, we can say, concept that we had to the digitization and sampling, quantization, which is more important in the digital world. Let us talk more regarding about the concept of intensity level resolution, which is the number of the intensity level which used to represent the image. And the more intensity level used, the finer the level details of the sculpture on an image, and intensity level resolution usually give in terms of number of bits, as already we taught, but we can also see here. Suppose if the number of bits is 1, the number of intensity is 2. If number is 2, then the number of intensity is 4, and if it's 16, then the number of intensity is 536,000 as the number of intensity level. Let us see the example. Suppose 256 gray level with the 8 bit per pixel can be the image. Then you will see that 286 gray level, 64 gray level, and 32 till 2 gray level, means that 1 bit per pixel image quality can be as the output. Maybe some of you tell me that it's not useful, it's wrong. It has its own value, but it has less detail. Let us talk like that. As much as your resolution comes down, maybe it has less detail. That is why maybe when you want to load some document for any work, suppose for your visa application or any process, they tell you that your resolution or your DPI should be like this much, 300, 200, 200, 250, something like that, some value like this they will give you, because they know that their system can recognize till this much resolution. It's a very critical concept. One more thing that you should know, it's about the saturation and noise, which we call saturation as the highest intensity value above which colors is washed out. And we know the noise as the grainy texture pattern. See here, suppose in my figure that I have, or I take the pictures, digital image here, you will see that I have some saturation here and some noise which shows as the edge part. Then it's showing me here that maybe some wrong info or maybe some data which I cannot use them. But one question will arise in our mind that how much resolution is enough? This is the big question with resolution. It's always, all people tell us, what is your image resolution when you do some research? Really, this depends on image details and what you would like to do with that, means that application. Does image look some pleasing and some can you see what you need to find in this image like that? This is something that you should have in your mind. Let's see these two car figure. If my resolution is like the right side figure, you will see that picture on the right side is okay for counting the number of the car, but not for reading the number of the plate. Okay. If I want to read the number of plate as my application, then the left side is okay. But if I want just to count how many cars are moving on the road, then the right side is completely okay. I don't need high resolution. Then if I say the resolution this much is okay, maybe through the first task that I tell you or I give you and some of you send that, you see that the number of some number or some value for the camera resolution, which it shows that, okay, what should be the application and from which application we can use this type of cameras. See more about low detail and medium details image also. You will see that the Lena feature, this woman picture, as the standard form, it has the low detail, which the medium details is this two. I tell you, these two figures are more standard figure in the image processing world, and most of the researchers use them. One more thing regarding the image is the format of image, which next lecture when we are going to work with the MATLAB, we should have it in our mind that which type of file format we have. Most of you work with this part. I'm not going to talk more, but have it hundred of image file format we have. But the famous one is TIFF, which has the tag image file format, graphic interchange GIF, portable network PNG and JPG, which we have. And image pixel value can be between 0 to 55, but in the grayscale, in the binary, it should be 0 to 1, and in RGB, it can be 0 to 5 to 55 with some other color models. And see that it can be variable. Please have this in your mind. We will work more when we see them in the MATLAB board. Okay, I don't expect that you memorize them. Nothing to memorize. Just have this idea that grayscale or intensity image with one channel, it has these bits pixel with the range, and also compare them with the color image and spatial image. Okay, you will see the difference between the range and bit per pixel as the comparing value here, and we have the different variety of them. Have these table in your mind. We should see that how many bit per image elements we have. We will compare them in the time of working with MATLAB. Okay. One more concept that today I want to talk as the last part of today's lecture. This is the dithering. That let us see what is this concept meaning. Dithering is the technique to simulate the display of colors that are not available in the current gray scale or current palette of display device. Generally, full set of colors is usually represented with a reduced number of the intensation. And this accomplished by arranging the adjacent pixel of different colors into the pattern, which simulates the colors that are not available. Dithering become possible because human eyes only average over an area and a property known as a spatial integration we have. Then for this dithering, we have some method which we call it thresholding, classical halftoning, random dither, and patterning, and oriented dither, and error diffusion. Dithering threshold is have some meaning like that. You know, threshold is chosen be in the middle of grayscale of source image, and the pixel in the source image darker than this threshold value are replaced with black, and those lighter than in the white. As you see here, we have some step function, which is between 0 to 1, or we can call between dark to light in the y direction, and in the x direction, dark to light one. As you see that here, I have some figure, it's some statue, something like that. And then you will see that after doing the threshold, I make some uniform between the image that you will see some darker part and some white part, which come here, which is related to the threshold value that I choose. Okay, it's something like exam. We say that after this mark, people will pass, and before that, people will fail. Okay, threshold is nothing by that. Then classical halftoning is another method which different intensities or gray level are represented by dots of varying size and pattern. This halftoning is also used for printing the color pictures that nowadays it's one of the fantastic job people will do. And the general idea is same by varying the density of 4 secondary printing color, cyan, magenta, and yellow and black, as the abbreviation of CMYK. Maybe you see this word on Photoshop when you work with CMYK like that. This is exactly the method for dithering, which they will try to make the black color or gray color into the colored one. And any particular shade can be reproduced with this method. You will see that gray halftoning and color halftoning, which I shown here. And now you have some color at the end of the box that you see. Some random dither we have, which is the random dither is the random amount of noise which is added to source image, and threshold is applied. Some patterning we have, which for each possible pixel, or it can be some group of pixel in the source of image, a pattern of pixel that approximate that value is created and displayed. Remembering the concept of spatial integration, if approximate patterns are chosen, the appearance of various intensity level, these can be simulated. And order details, which in that patterning is achieved with one-to-one mapping between pixel in source image and pattern pixel. This eliminates the spatial distortion due to the spatial enlargement and subsequent loss of spatial resolution in patterning technique. Error diffusion is also another way. For each possible pixel in source image, a closest value available intensity or color is identified, and the difference between the source image pixel value and the closest value available intensity will be calculated. This error is then distributed to some neighbors of this pixel before their closest available colors are identified. You will see here I have 8-bit original pictures, then with the threshold of 1 bit, random of 1 bit, order deter, and error diffusion. These are the acts which I have done on this photo. And soon, with the help of MATLAB, also we will review all these concepts and compare them. Okay, I wanted to teach you the transform an image transform, but I think now it will take long time, and because we have some problem, we couldn't finish. But from next lecture, I will do the image transformation, and then we have the MATLAB session, which is very important part. For this week, we should finish these two parts. Then the task for the MATLABs and so on will come to picture.